Hello and welcome back. Today we're going to look at polar coordinates, and a polar curve is constructed on the polar coordinate system. The polar curves are defined by points that have a distance from the origin, which we call the pole, and depend on the angle measured off the positive x-axis. So we can actually use polar curves to describe familiar Cartesian shapes like lines, ellipses, but they're very useful to describe unfamiliar shapes like cardioids, lemniscates, and the butterfly curve. So Cartesian graphs are useful to describe horizontal and vertical distance, whereas polar curves are useful to describe paths which have an absolute distance from a certain point. So one practical use of polar curves is to describe directional microphone pickup patterns. So a directional microphone will pick up different qualities of sound depending on the location the sound is coming from outside the microphone. So a cardioid microphone has a pickup pattern in the shape of a cardioid. So you can see combinations of the three basic patterns, cardioid, figure eight, and omni, with the bidirectional here, supercardioid, shotgun, and hypercardioid. Now let's look at the polar coordinate system, which won't be too difficult considering that you already know a lot of trigonometry. So to form the polar coordinate in the plane, we have a fixed point O, which is the pole or the origin. And we construct from O a ray called the polar axis. So each point P in that plane can be assigned polar coordinates r theta. So r, again, like the radius, is the distance from O to P. And theta would be that directed angle, again going counterclockwise to the ray OP. So rectangular coordinates are unique. So when we think of the Cartesian plane, we could have 5, 7, 500, 700. They're going to be different. But polar coordinates are not unique. They're going to be modular or cyclical. So thinking of a full rotation and coterminal angles, we can add or subtract 2 pi n. Again, the pole is represented by 0 theta. For example 1, let's plot these points and find 2 additional polar representations. With a radius of 3 and an angle of negative pi over 3, we would know that that would be in the 4th quadrant, so it would be here. If we want to find another representation, we can add 2 pi to theta, again find the coterminal angle, so that'll be 5 pi over 3. We could also start with negative 3 as our polar axis and think of the rotation from the negative x-axis. So that would be negative 3, 2 pi over 3. Now for 2 pi over 6, that would be in the 1st quadrant, so that would be B. To find another representation, we'll have radius of 2 and subtract 2 pi, we'll have negative 11 pi over 6. Or we could have negative 2 for our radius. We could think of this rotation. So that would be 7 pi over 6. For the last polar coordinate, so negative 1 pi over 4 would take us into the 3rd quadrant. So this would be C. To find another representation, we can start with a positive radius of 1. That rotation would be 5 pi over 4. Or 1 with a negative rotation, negative 3 pi over 4. Now let's look at how we can convert polar coordinates to rectangular coordinates and vice versa. So just going back to the basics, we know that sine of theta is y over r, and cosine of theta is x over r, and tangent of theta is y over x. Now if we multiply both sides by r for these two equations, we'll get x equals r times the cosine of theta, and y equals r times the sine of theta. So converting polar to rectangular, vice versa, make sure we have these equations handy, and r squared equals x squared plus y squared. All right, let's look at example 2. So 4 pi over 2. Again, we know that that would be directly above the origin with a radius of 4. We know that x would be 4 cosine pi over 2. Y would be 4 sine pi over 2. And we can easily see that's going to be 0, 4. Thinking of 2 pi over 6 and be in the first quadrant, so we know that x-coordinate would be 2 cosine pi over 6, and the y-coordinate would be 2 sine pi over 6. We know cosine of pi over 6 is root 3 over 2, and we know sine of pi over 6 is 1/2, so this will just be root 3, 1. Now let's convert rectangular coordinates to polar coordinates. Well, 2, 2, we know would be about there in the first quadrant, and we know tangent of theta, well, that would equal 1, so the angle must be 45 degrees or pi over 4. We know the radius would just be, we could use a squared plus b squared equals c squared, right? So that'd just be 4 plus 4, or 2 root 2. So the polar coordinate would be 2 root 2 pi over 4. Now let's look at the next one. -1, 0, which would be right here on the negative x-axis. So we can easily see the radius is 1, and that rotation would just be pi. So the polar coordinate would be 1 pi. Okay, let's convert equations from rectangular to polar form and polar form to rectangular. When we convert rectangular equations into polar form, we just need to substitute in r cosine theta for x and r sine of theta for y. So for the first one, we'll have r sine theta equals r cosine theta squared. So I'm just going to simplify this, divide by r, so we'll get sine of theta equals r cosine squared theta. Now we want to isolate r, so if we divide both sides by cosine squared, we'll have sine of theta over cosine squared of theta, which we can rewrite as 1 over cosine theta times sine over cosine. So r will equal secant of theta times the tangent of theta. All right, for the next one, again, I'm going to replace x with r cosine theta and y with r sine of theta. We have 2r squared cosine theta sine theta. We want to isolate r squared, so we have 1 over 2 cosine theta sine theta. Now going back to some of the trigonometric identities, we know that 2 cosine theta times sine theta is going to be sine of 2 theta. So we can write r squared will be equal to the cosecant of 2 theta. Now let's convert each polar equation into a rectangular equation. So for the first one, I'll just sketch it. So r equals 1. Well, you can see right away that that's going to be a circle. So thinking back to the equations, we know that r is equal to the square root of x squared plus y squared. If we square both sides, we'll get x squared plus y squared equals 1. But if theta is equal to pi over 4, that means it doesn't matter what the radius is, the angle will always be pi over 4. We know the tangent of that angle equals y over x, or the slope. So the tangent of pi over 4 is just 1. So the equation will just be y equals x. Now for the next two, it'll take a little bit more problem solving. We could change cosecant into 1 over sine of theta, and then multiply both sides by sine of theta. So we'll have r sine of theta equals 1. And we know r sine of theta is y. So the equation would be y equals 1. For the last one, again, it's going to take a little bit of problem solving, but I'm going to change cosecant into 1 over sine of 2 theta. So I'll multiply both sides by sine of 2 theta. So r of sine of 2 theta will equal 3. Now we just saw that double angle, so we know that sine of 2 theta is 2 times the cosine of theta times the sine of theta. X is going to equal r cosine theta and y equals r sine of theta. So it would actually be a good idea to multiply both sides by r. If I separate these, we'll have 2 r times cosine theta, and then r times sine of theta equals 3r. Now we can start substituting. So we know that r cosine theta will be x, r sine of theta will equal y, and then r is going to be the square root of x squared plus y squared. Now we can get rid of that square root just by squaring both sides. So we'll get 4 x squared y squared equals 9 times x squared plus y squared. There isn't another way to write that nicely, so we'll just keep it in that form. Well, that's it for today. We'll go over more problems together in class.